All right, so I'm going to be walking through some more details on the frame. There's some intricacies on the suspension that if Jarrett's around when I get to that point, I'm going to invite him up here to help out with this. But let's go ahead and jump into it. Let's see what we're going to talk about. So you're going to see this picture a lot. That's the old Houston team that I lost track of how many events they won. But we're going to talk about materials. I'm going to talk about the ever-controversial safety cell, roll bar, and crush zones. We're going to go through suspension and steering with an assist from Jarrett, and then we'll talk a little bit about wheels and brakes. These are things that have already been highlighted in some of the more specific presentations yesterday. And I think it just occurs to me how great these visuals are going to be, especially for those that are like 3 rows back with the sun right in your face right now. But hey, at least you get some sun while you're here. All right. I had mentioned yesterday when we started talking about solar cars that I thought mild steel was an excellent way for a new team to begin, and I firmly believe in that. There's a couple of things here, like talking about it being inexpensive, less than $1 a foot. Steel has gotten more expensive since we originally wrote that number in there. I don't think it's necessarily under $1 a foot, but it's still cheaper than just about any other material, any other metal that you might try and use for your solar car. It is really easy to work with. You can get a MIG welder for a couple $100. Side note on that, if you're going to get a MIG welder, there are 2 options for you. You can get welding wire that comes with a flux core that as it melts the wire, this slag covers the weld and keeps the oxygen from contaminating it and creating these little volcano-looking things during your weld. Please don't do that. If you can, spend a little bit of extra money, get what they call gold gas or the MIG welder, mix gas cylinder and a gas shield for it. That will keep all the oxygen away when you're welding the steel, and you will end up with beautiful, clean welds without any slag, any little volcanoes or things like that. And the last time I taught somebody to MIG weld, to get them to do an easier weld where you had 2 pieces kind of just at a right angle to each other laying flat, it took about 15 minutes to explain to them how to do it. This is why this is so powerful. You literally only need a chop saw, an angle grinder, and a MIG welder, and you can build just about anything out of steel. Well, maybe a drill if you want to put holes in it, or a drill press if you want to put holes in it without like yanking your arms off. Super easy to change and modify this stuff. Literally, we didn't like something on the car, we would get the Sawzall, we would lop that piece off, and take the angle grinder, smooth off the spot, and weld on a new piece. We'd lose about 20 minutes because inevitably we were not as wise as some of the lecturers here that have explained, you know, if you think it out and do drawings ahead of time, you'll be good. As William shared, we decided to rebuild our car in 6 weeks, which meant we were kind of planning on the fly, which meant that half the things I welded into the car, I welded in upside down or backwards and ended up having to do it multiple times. As you also heard, that's one of the penalties for doing that. The point is that steel supports this. Yes, you will have a heavy car, but the trade-off is your car will be fairly indestructible. So that's most of what I have to say about steel. Again, for a first-year team, I highly recommend this as a starting point. Some YouTube videos, a MIG welder, and a couple of tools, and you're ready to go. And just about everybody has a middle yard nearby that they can get to. Chromoly steel. So chromoly steel is just a different alloy, slightly different characteristics. Similar things, slightly different approaches you're going to take with welding. And as we heard yesterday, since it is a different alloy, you do have some other complications with it. Like it is a little bit, and you guys can correct me if I'm wrong on this, I believe chromoly is just a little bit more brittle, and you can get a little bit easier stress fractures going in it. The trade-off, though, is it's much lighter than mild steel. So, for the strength to weight ratio, if you want to get set up to do chromoly, you get a little bit of a benefit there. It is more expensive. The takeaway from that, I mean, at the time that we wrote this, it was $4 a foot versus $1 a foot, so about 4 times the price of mild steel. Don't quote me on that, but it is more expensive. So you can get something that's a little bit lighter. Again, I would recommend this for a team that's second year and beyond, or a team that's got a lot of experience with metallurgy and welding, because it is a little bit more complicated, a little bit more thought has to go into it and the design. However, it's out there. Chromoly is pretty good stuff if you're trying to still have a structural car that's pretty easy to put together and lighter than mild steel. And these days you can get steel, chromoly, and all these materials from either vendors online or your local metal yard in pretty much whatever size and configuration you need. It's not hard to find that stuff for solar cars. Aluminum. Our second year, we decided that we had advanced past the point of using mild steel. So we went to 6061 T6 aircraft grade aluminum and got a TIG welder. And boy, was that an experience learning how to TIG weld. It is completely different than MIG welding, although for aluminum, you can buy kind of the equivalent of a MIG welder where it'll auto spool the aluminum wire into the weld versus you doing it by hand. It was actually really fun. I enjoy welding, but it is another skill. So if you are thinking about doing something like aluminum, which again, much lighter than steel, depending on the alloy that you use and the configuration of it, you notice that there's a lot of trussing in this car right there. Trussing meaning that we've got different triangles, different framing, supporting stuff. Nothing is just an open box with 4 sides. Any type of open box with 4 sides is going to be very flexible and non-rigid. And that is one of the trade-offs with aluminum pipes. Depending on the alloy, you can get a lot of flex into it. They aren't quite as stiff as some of the other materials out there. The 6061 T6, I want to say, is actually a pretty stiff alloy of aluminum. Again, if you guys, and those of you that are watching this online, are looking at Wikipedia right now, can correct me if I'm wrong in what I'm saying there, because I'm pulling this from memory from almost 25 years ago. The takeaway for aluminum, again, is it's a much lighter material than steel. It does take a little bit more work, and the gotcha that you need to think about is if you're not doing a lot of testing with your car and you come to the solar car race and something breaks, something fails, or we say, you know what, that crush zone needs a little bit more material on it, you need to think about how you're going to be welding it at the event. With whatever material, this is a hint for every team out there, for whatever material you choose for the body of your car, be prepared when you get to the race, seriously, be prepared when you get to the race to make modifications to it. If you have no way of adding something or removing something, and I know carbon fiber, yes, that's a little bit different, but we tend to talk to you a little bit more for most of the teams that are doing monocoque carbon fiber chassis or monocoque chassis in general. But be prepared for if you have to change something or something fails. If you did not put 500 miles on your car before you came to the event, be prepared for something to break during the event, and how are you going to reattach it and reinforce it? If you don't think about that, I guarantee you will lose at least a day in the event. And that takes you sort of out of the running of the competition for a trophy, if that's something that motivates you. Also, you run the risk of having it break during scrutineering and not being able to enter the event. So just plan ahead. The teams that bring their welders, bring their tools to do that are the ones that are most successful, and honestly, they're a huge help to some of the other teams that weren't able to do that at times. So again, I've warned you guys in the past, I don't stay on topic very well, so you're going to get more of a stream of consciousness than just talking simply about aluminum frames. So sorry, you guys have to deal with it. Hasn't quite been enough caffeine yet this morning. All right, so talked about the difficult to repair. There's the comment about resisting fatigue on there. Aluminum, if you take a thin aluminum bar and you bend it back and forth multiple times, eventually it'll snap right in the middle. That's why we don't have a lot of aluminum springs. That's more of a side note. What I want you guys to take away is not necessarily worrying about resisting fatigue. I want you guys to understand that if you're going to build something out of aluminum, it does require a lot of trussing in between to make it stiff and rigid and do what you want it to do. And it will still be super duper light. I think our aluminum car, all told, was around, well, the frame itself was, I want to say, about 30 pounds, the entire frame of our car. Mind you, that was in the late 90s, so the rules weren't quite the same, and our car was called the Rolling Coffin. But that's the benefit of aluminum. Carbon fiber. All right, so you want to kick it up a notch, and you want to do what some of the colleges and professional teams are doing. That is carbon fiber. Quite possibly, it is the lightest and stiffest material out there that you're going to find. You know, it's on par with steel. Carbon fiber is just like freaking some type of miraculous composite material with its characteristics. We do require, if you're going to build a carbon fiber body, remember this, that you have to do destructive testing on the material and submit us the results. That is important. That's how we can reassure ourselves that the material you chose and the way you're doing your layups are adequately strong for the body of the car. Because remember, in a monocoque design with carbon fiber, the entire body is the structure of your car. That's everything. It's your crush zone, it's your support frame, it's everything. So we make you do destructive testing on a sample of it and return us the results. So heads up on that. You can literally form carbon fiber into any shape you can think of. I would invite you guys to go back to, I think, last year's presentation or the previous presentation with Mark Westlake doing some of the talk, or Lee Cabe. Both of them have a lot of materials experience with doing composites, making molds, making plugs. You can also talk to the Iron Lions team. They're doing a lot of really cool cutting edge stuff with carbon fiber and even 3D printing plugs for their molds. So there is information out there, but heads up, this is a kind of critical one that should be in bold. The learning curve is steep. I would not recommend this for a brand new team. This is something after you've had a little bit of time trying out a car design, seeing what works, what doesn't, and then again, you want to take it up to the next level, move into the advanced division, do that kind of thing. You can see how there's the bracing on this are basically pieces of carbon fiber that are bonded inside of the body to increase the stiffness and rigidity. You can see kind of, it's hard from this picture to see how they did the mounting plates and things like that, the pickups for the motor. You have to put a lot more thought into the internals of this than something like mild steel, where it's just, hey, we got to mount the motor. Okay, well, weld another bar over here. Hey, look, it's our motor mount. You can't quite do that as easily with carbon fiber. You need to think that out a little bit. Also note that there's a number of teams that I've seen with their first time advanced carbon fiber car monocoque design that have gone and pushed the edge with technology and lightweight and have a failure. And those kind of failures tend to be multiple day failures. This is something I want to get across. If you want to do this, just heads up, test your car. I don't think I said that before. Did I say test your car before you show up to scrutineering? Like at least 500 miles. Because that's how you find out when things fail on the road, where you can actually still do something about it. Some of the teams that brought these advanced cars, and I've seen a handful of them over the last, I'll just say the last 10 years, have had failures, and again, it's multiple days or it's a race-ending event for them, and I don't want to see that. So plan ahead, plan accordingly. If you're going to take on a project like this where you want to go advanced technology and advanced composites, give yourself time so you can test the thing. All right, I think we kind of covered that one. Let's see, what are we going to talk about now? Oh, yes, let's get into something really controversial. Is everybody awake yet? No, I know this is the most exciting topic we're going to hear, especially following Texas A&M, where they got to talk about cool stuff. I'm going to talk to you about safety rules. All right, safety cell. Does everybody know what a safety cell is? Like, can I see a show of hands if you think you know what a safety cell is? All right. There's about half of you. So let's think F1, let's think NASCAR, the safety cell. It is the rigid structural part that protects the driver. Have you guys ever seen one of those really glorious crashes where the car kind of just disintegrates at like 200 miles an hour, and then like 30 seconds later, the driver just like walks out of what's left of the wreckage unharmed? That's because of the safety cell. That is the part of the car that did not disintegrate, that was around the driver to protect them. It is typically stronger material, more rigid. It's not meant to flex or give in the event of an impact. It's meant to protect the driver. So, for the safety cell, which we used to call the roll cage, we specify a minimum outer diameter of the tubing of 1.9 centimeters. And we specify a minimum clearance. Okay. When we say that there's a minimum clearance of 5 centimeters, if you put your smallest driver in there and you have 5.002 centimeters, you are probably screwed. When we say minimum, it means overshoot that number by a little bit. Give yourself 6.5, so that when your larger driver gets in there and we look at his shoulders, I don't have to tell him that he can't drive the car because he's got under 5 centimeters of clearance. We ask for 5 centimeters of clearance, and we ask for a minimum size of the internal tubing on the car. I'm going to walk over here for a second, and I'll lose the microphone so I'll talk a little bit louder. But can you guys see on this car right here that we've got a whole bunch of lightweight structure on the outside, which that's going to be the crush zone, but then we've got heavy-duty material for a roll bar and heavy framing around the driver. This heavy stuff is what we call the safety cell. It used to be called the roll cage. It's the part that's meant to protect you and keep you safe. If the rest of the car crushes, the thing that's going to stop crushing is the part right next to you. And that's also why we ask for a little bit of clearance. If somebody does T-bone this car, the crush zone's meant to actually crush and safely absorb the energy. Instead of it going to squishing you, the energy goes to just forming the little lightweight material, and then all of a sudden, you've got significant structure there that keeps you intact and just causes the car to slide with. Anyways, the heavy material is the safety cell part of the car. The light material is the crush zone part of the car. And the big hoop that goes over the top like this, that's what we refer to as the roll bar. It's meant to keep you from being squashed if the car ever turns upside down. So, crush zone, squishy bit, meant to absorb the energy of an impact. Roll bar, keep you from getting squished if you go upside down. And safety cage, again, keep you from getting crushed if something ever comes from you at the side after it gets through the crush zone. So, big tubing for safety cell, smaller stuff for crush zone, big tube for roll bar. So where I'm going with all this, we legislate in the rules that we need the minimum of 1.9 centimeters. Well, what if you tell me I'm using a different material or I want to do something different and we're actually using something slightly smaller? You can request a waiver for this, but you need to show me your CAD drawings and what you want to do, because I truly, truly care about what you're designing that's going to protect your driver. And I know all the advisors and sponsors here also care about that. And I know most of the people that are going to be driving the car probably care about that. I know it may not be your top concern, but trust me, once you're in the car going down a country road at like 50 plus miles an hour, you will start thinking about what's around you actually holding you up and keeping you from sliding on the road. You can request a waiver if you want to do something different than that, but we have to talk about it and make sure you're basically giving some equivalent structure and strength. This is engineering. The size of the material matters less than the way you actually plan to use it. That's why we give you the ability to ask for waivers and why we talk through it. You can make something equivalently strong with lighter, thinner material, but it depends on the configuration, the trussing, and things like that. Roll bars. Remember, this came up yesterday. I'm going to give you another hint and another secret that the materials we request, minimum OD of 5 centimeters, it's 2 inches, inch-ish. That's already right off the bat kind of hard for, like, if you go to an exhaust shop, for them to bend something like that unless it's super thin. We also specify a minimum thickness for that. And if you guys are struggling to find somebody that can bend that type of material, well, that's another opportunity to come talk to us about a roll bar waiver. The team here is using something lighter than that, out of aluminum, but they've also attached significant bracing and some other things to it. If you want to try and use an alternate material, we can do that, and we can talk about how you're going to brace it and how you're going to support it so that that lighter material would do the same job of the heavier stuff. That's fine. Once we get to that point, and we will work with you on it, I will work with you on it. Once we get to the point that you've basically got something equivalent, you're good to go. So please, remember the waiver section of this.
Chris.
Yes?
As you're talking about the waivers, one of the things you need to explain to everybody is they have to designate that what they are proposing is equal to or better than what's provided.
Yes.
It can't be less.
Thank you for that. So, for those of you that couldn't hear Dr. Marks, I haven't explicitly stated this. If you request a waiver, you have to tell us what you're proposing, and you have to explain to us that it is at least as good or better than what was originally stated in the rule. The intent is that you meet the spirit of the rule, which was we are trying to protect you, we are trying to do something specific with this. So if it's for your safety cell, if it's for the roll bar, explain to us why you believe it's better and okay. That's the very first part of this waiver process. You say, we would like to get a waiver for the roll bar for the outer diameter of 5 centimeters or for the wall thickness of so-and-so, because we are using this material and we propose to use it in this configuration where we think it will be just as strong or better than what we could have done with that first material. And then show us the drawings and say, this is why. That's what we're looking to do. Does it mean that you have to do a bunch of engineering calcs on top of it? No, but you do need to walk us through why you think it's okay to do that in place of the rules. And that's where we go back and work with you on it. And if we agree, you get the record that you can take to scrutineering, and they'll sign off on that one based on that email record that you have. By the way, if you are ever granted a waiver, hint, hint, save the email. And they're not good for year to year. Every year you have to do it again. Just because you got a waiver 6 years ago doesn't mean that it's good for this year's race. I get that a lot with teams. It's like, but you said when we asked you about this, and you missed it last year, but 3 years ago we asked, no, every year you have to resubmit that waiver to requalify that car. Do you?
Yeah, I was going to add, I'd also print it out and bring it to the station 1 and 2 if it's any sort of waiver, because the lead judge or whoever's judging your car for scrutineering will ask for waivers or things like that if they see something that doesn't comply with the rules. So.
Absolutely, and William will cover this a little bit too when he gets through the rules section as a reminder about that. So, takeaways for a waiver. I know we got off on a little bit of tangent, but a waiver, it allows you an exemption from the rule. You have to explain why you think what you're doing as good or better than the rule, and if we approve it, save the email, print it, and bring it to scrutineering. Thank you for finishing the thought for me on that. That's what I meant to get to, but I didn't say it. Yeah, and then you'll get hung up at the stations while you try and figure out where you can find a printer to go get the email. Okay, so I ran through this really quickly, but we specify how do we measure these things? What are the minimum requirements? We typically look in distance from the driver. If it's a minimum, if something is a minimum dimension, I'm going to measure it from outside to outside, okay? So that we'll give you the benefit of the outside of the tube to the outside of the tube. Like there's a minimum height for the crush zones or a minimum width of the crush zones. And I'll get into that more. Actually, I've got a better diagram for that. I'm skipping ahead. This is focusing on material sizes. Crush zone. So we've got all this stuff in this picture down here on the bottom right. And we say that you have to have a minimum of 15 centimeters of clearance to the outside of the safety cell. Outside of the safety cell. So, what was the safety cell? The big heavy material. From the outside of the big heavy material to the outside of what you're calling your crush zone has to be 15 centimeters. 15 centimeters is what, 6 inches? That's not a lot of space, okay? It's not huge. That's the minimum. Please check this. There's no give on this. If you don't meet that, you have to go back and add more material to the car. These are important rules. Everything in Section 5 is critical. I mean, I highly recommend you take the rule packet, at least Section 5, slip it underneath your pillow at night, so if nothing else, you can absorb it by osmosis. Section 5 is important. Yeah, we had a biology teacher that used to tell that to us. Put it under your pillow and absorb it by osmosis. Here's what I'm referring to about minimum dimensions, like this 30 centimeters here. When we actually measure it, it will be from the outside to the outside, okay? The outside to the outside of the tube. Let's see. Let me focus on the main point of this. This is straight out of the rule book too. Does this mean your design has to look like this? Lord, no, it doesn't. But this is us, again, trying through a rules document to explain what we're looking for, which is a very hard thing to do. All we're trying to show is a few things in this. One, that you've got a big roll bar here that's a solid piece of the car that, look, extends above the driver's head. The roll bar has to extend above the driver's head and has to have the minimum, that 5 centimeters of clearance. Where does that 5 centimeters of clearance measure? From the top of the driver's head, I lost my little laser pointer, to the inside of that tube. There has to be at least 5 centimeters of room. Okay, that's only 2 inches. There has to be at least 2 inches there. You have to have a big giant roll bar, or you have to submit a waiver. Safety cells, your crush zone. Your crush zone is in light green here. We tried to show you, the minimum height thing here, the minimum distance. In this case, the safety cell is blue. The crush zone is green. And look, we're trying to show you that there's a minimum of 15 centimeters from the outside of this blue to the inside of this crush zone piece. We're also, the minimum height for the left and right side of the crush zone is 30 centimeters, so we're trying to show you that. And again, in the back, we're trying to also show this 15 centimeter dimension. There's also this drawing on the side over here where, again, this is like, pretend you're looking top down at it, and we simplify the view. The safety cell is just that blue rectangle. Look, all the way around, you need to have that 15 centimeters for your crush zone. What counts as crush zone on the front of the car versus the sides of the car, that's something we can talk about. Typically, the places where it's really narrow is the side of the car next to the driver. In the front of the car, you've got pedal assemblies, you've got wheels, you've got more things. We typically don't see crush zone issues there. Where I see crush zones a lot, issues with them, is along the side of the car. The other thing is, notice how we have safety cell going all the way along the vertical position of the driver. It's not just simply wide open. I have seen a number of cars that when you have the driver sitting in it, like on this slide here, there's literally nothing next to the driver. There is not a single bar, which means that if you're going down the road and you get a Ford Expedition with a bumper that's way off the ground and they accidentally sideswipe you, the first thing that's going to stop the bumper is likely the driver's elbow, which is why we ask for extra structure to be in here. I recognize that this sometimes makes it more challenging to get out of the car. Luckily, you all are in high school and you're fairly nimble, so you will be able to figure it out. But put something there to protect the driver so it's not completely open and you can't just drive a car right into the side of it. My example is the Expedition or another solar car that's maybe a little higher off the ground. I don't want the driver to be the first thing that the car touches. All right, so that's a very common one during scrutineering. We miss on the dimensions of crush zones when we measure it, and we don't have any protection for the driver. Their entire upper body is just exposed, hanging out there. And again, this is not the only way you can do this design. It's just us trying to illustrate the picture. Do not fall into the trap of thinking that my car has to look like what this diagram is. It does not. It does not. You can do other things. So now everybody in this room understands what a crush zone is. It's the squishy part that's meant to absorb energy in an impact. The safety cell, it's meant to be the rigid part that protects the driver, so if the car disintegrates around them, that part still stays there and it keeps the driver safe. The roll bar is the big hoop that's going to go over the driver and keep them from getting squished if the car goes upside down. All right? I've now beat this to death, and I will listen to those two over there who are yelling at me to move along faster. I'm sorry, I thought these things are pretty important topics. All right, we already talked about this. There's another example in here where it's kind of illustrating where the crush zone is, where the safety cell is, and you can see the roll bar in here. Again, note that these are different configurations, and this is lighter material, but there's also dual roll bars, and there's another piece that goes over here. So this is why we have waivers. More roll bar examples. Again, some of these are older roll bars before where the rule changes, but notice that we still have the clearance here. And again, this is a delta configuration where we have, a different configuration than a simple hoop because we have other material coming up to it and supporting it. That isn't a case where you could probably get a waiver for it. So note here, in bold and blue, use the waiver process, Rule 5.21. I talked about this to death, but here's an example of something that is less okay at this point. If this was a car that had a carbon fiber body draped over it, it would be fine. If this is the only material on the frame and you're calling a single piece of tube out here your crush zone, it has no depth. It does nothing unless somebody hits exactly at the height of that tube. This is a case where if you showed up to scrutineering, I would tell you, yeah, you guys are going to have to weld more material on that. That's not a crush zone. So, one bar simply hanging off the side of your car does not make a crush zone. And if you look, it's the same exact material as the safety cell. The only reason they called it a crush zone is because they put no bracing in there. This is an example of a little less of what's ideal. This would need work. Again, if you have a carbon fiber body and this is just meant to be a lightweight frame to pick up part of the shell, then that's a different story because you have the carbon fiber body to do something. All right, moving along. We're going to talk about suspension and some of the other stuff, and this is where I'm going to give it to Jarrett, who's going to make up all the time that I wasted talking about other stuff.
So just to add one note to his crush zones things, steel is not the only method for building a crush zone. We see a lot of cars where people have welded a bunch of random little pieces of metal to the side of their car to call it a crush zone, and they're tacked on with a single weld or something like that, and it actually makes the car more dangerous. So sheet metal makes great crush zones. The pink foam insulation makes great crush zones. So there are lots of ways to skin that cat besides just welding little tubes to the side of your car. In fact, if you go to the speedway, behind the wall that NASCARs run into at 200 miles an hour, there's 12 inches of pink home insulation. Same thing you buy at Home Depot. So just other options for lightweight ways to make those crush zones. And with that, I swear we'll move on from crush zones because we have beat that horse to death a few times. Okay, so now we're moving on to suspension. So what's the purpose of the suspension of your car? Well, it's to minimize the shock to the driver and the car. Really, the important part is the car, not the driver. Though it provides some for the comfort of the driver, because if you're in this thing for 8 hours in the Texas sun, if you're getting beat to death, the odds of you doing a good job, as Shannon talked about yesterday, as a good driver are pretty slim. The real purpose of the suspension is to interact with the road and to allow your car to perform as it's supposed to. We are literally talking about the point where the rubber meets the road. This is the only way that your car interacts with the road for steering, acceleration, braking. So when you do your tilt and turn test, your suspension determines whether or not you're going to pass that test. When you go over a bump on the track, it determines if you're going to go driving into the wall or take a nice lap through our infield, or if you can continue on smartly and go as you expected. Okay, so some of the just common terms so that we're all speaking on the same page when we talk about terms for the suspension. So on the left here you have the spindle, which is the part that connects all your moving parts together. And it includes the hub, which is the rotating portion that connects your tire to the car, the axle, which is the non-rotating part that's connected to the car, And it also connects with your tie rod, which connects your steering to the car. You put the hub and the axle together, you have a spindle, and it connects your tie rod, and you have a suspension. There are a couple common types of suspension that you see a lot. The first one is the McPherson strut. The McPherson strut, the suspension, the shock is actually an integral member of the suspension component. This is something you see on a lot of your light cars, or your small cars. It would be very common into it. We've also got a solid axle. This has been the traditional suspension system since, well, horse and buggy. Some of the original Roman chariots had a solid axle and a leaf spring-tight suspension. And finally, you have the double A-arm suspension, probably the most common suspension that you're going to see in racing. And each one of them has pros and cons. And unfortunately, I'm not here to tell you what the right answer is or even what the best answer is, because every one of these suspension systems have pluses and minuses. And there is no right answer. What answer is what works for you. And again, in a few minutes, I'm going to talk about setting up your steering geometry and suspension. So I'll tell a quick story. When I was in college, one of the ways I made money working through college was setting up race car suspensions for very expensive, mainly GT cars. A good friend of mine that I grew up with had a friend in Atlanta. I went to Georgia Tech, so that's missing part. And he hooked me up with one of his friends who was a neurosurgeon in Atlanta. This guy had a midlife crisis, went out and bought a Porsche, started racing it. Turned out he was really good, and so he went out and bought another one, the GT3R, and was actually campaigning fairly seriously racing. And I did most of his setup work for him. Well, his son had the second car, and basically there are rules on how you should set up a car. There are best practices. And people make lots of money. That's an entire industry in crew chiefs for F1, NASCAR, and how to set up a car. But those are minor tweaks. There are general rules for how you set up a car. Well, for John's car, his son, he set up his car completely wrong. And no one else could drive that car. He actually had neutral toe, border ion slightly out. So the car was incredibly twitchy, but it would dive into a corner. But on a straight, it wanted to go all over the place. And so I was driving his car one day, and I ended up running it into the wall and turned 12 at Road Atlanta, because coming out of the corner, I couldn't get the car back under control. But it worked for him. He was the national champion in SCCA for the Porsche class, and I brought the exact class. So the moral of the story is, the right answer is what works for you, and a combination of what materials you have, the budget you have, the skills you have, and run. So with that, the McPherson system is pretty easy to build. There's not a lot of adjustment to it. You go find one at the parts store, you buy it, you bolt it to the car. The downsides of it, it's very heavy. I mean, it's generally meant for a Honda Accord, not really something most solar cars. There's really not a lot of adjustability to it. It's set up. Might be able to change a little bit with some shims, move it here or there. But if you want to change something, you're going to have to cut something off the car and change its actual location. And generally, it doesn't have the best handling characteristics because it's made for a road car. The solid axle, ridiculously simple. You go to a Tractor Supply store, you can go pick one up for $100. Or it's a piece of tube. You can weld one together. Leaf springs have been around since the Roman times. They're well-known, readily available, and you can get them from everything from super lightweight and carbon fiber to hold up an 18-wheeler. I recommend more the lighter than the 18-wheeler, but so they're super easy to manufacture. You know how big your leaf spring is, 2 bolts, a couple of U-clamps, and you have a suspension. Downside is, again, they tend to be heavy. They're very hard to adjust. Well, there's very little adjustment once you bolt it together. And they generally don't ride that well, so there's not a lot of adjustment you can do to it, but it will get you down the road. If y'all were paying attention, yesterday with Crawley's car, their rear axle was a solid axle. We've had quite a few cars that have done very well with solid axles, so that works for people. The most common one we see is the double wishbone, double A-arm suspension. It's very versatile. You're limited by your imagination. You can build it in any configuration you want, and you have infinite variety to change the suspension parameters and make it do what you want. So that's why it's highly desirable, and you'll see it pretty much every race car in the world is set up with some variation on this. So very just. The downside is you have to design it. So if you don't design it right, you're kind of stuck with it. And it can be more difficult to manufacture and maintain. Again, it's custom to you, which is both a plus and a minus. And the final option is the no suspension at all. There's nothing in the rules that says you actually have to have a suspension. You could take that hub or take that spindle, weld it to the side of your car, and go down the road. And that is the lightest, cheapest option, obviously. However, it has some serious drawbacks. You would think the Texas Motor Speedway would be a nice, smooth surface. It's not. There are a lot of pits, craters, transitions in it, and you will get beat to death. And we've had an argument for many years about whether or not you could run without suspension, and we've seen people try it. And those cars tend to break because there's a lot of material fatigue, and then there's a lot of fatigue on the driver because they are getting shaken to death. But it is an option, and it might work. If you're going ultra minimalist, it might work for you. Okay. So suspension can be very complex, but we're not going to go down into a rabbit hole. And again, I'm not here to tell you the right answers. But one of those important things, and if we haven't taken this away from this yet, please let me stop my foot again. Design for strength and reliability. If your suspension doesn't get you around the track, it's useless. And if it breaks, we've had a lot of cars that have been sitting on the side of the road because their suspensions weren't designed appropriately. And the design for adjustability. If you want to make sure, if it's not working for you, that you can change it easily. If you have a AA arm suspension and you have rod ends in the end of it, if you need to move it a little bit, you can go unbolt some things, screw the rod end out, put the bolt back in. 5 minutes later, you've got an adjustment. Okay, some more terms. Because most people end up with the AA arm suspension, we're going to use the AA arm suspension as the example. However, these terms apply to pretty much all the suspension. So a couple of key terms that you're going to need. The first one is camber, and the camber is the angle of the wheel from the vertical. So if you can see the little dotted red line, that's the vertical. You're looking at the front of the car, looking back. So negative camber, your wheels are pointed kind of in. Positive, they're pointed kind of out. And your camber adjusts your grip, especially in corners and really at high-speed corners. It doesn't really have a lot of applicable in solar car racing. If you see the cars driving down the street with the super candid tires, sorry, they're idiots. NASCAR car runs about 2.5 degrees of negative camber, and they're traveling around a 27.5 degree bank at 212 miles an hour. In that case, the wheel actually rolls over and flattens out at the top of the bank, and it gives them additional stability. I have yet to see a solar car do that. We don't allow teams to drive on the bank in any case, and if any of y'all are driving 220 miles an hour, I'm running the other direction. So, not super applicable. Generally, you would want your tires to be as vertical as possible, but if you're going to erring to the negative side. Yes?
There is something important about this. If you're way off of neutral on your camber, what will happen is you will start wearing the side of your tire rather than the bottom of it. And if you're using the high-end solar car minimalist tires, what it means is you can feel that way sooner than you should have felt it if you actually had set a neutral camber for the car. So just be aware of that. It doesn't actually do anything for performance, but it will wear out your tire much faster if you've got it set up wrong.
Okay, so another one is scrub radius, and this is also very applicable to the low-profile solar car tires. Most cars, you don't think about this because you've got big, wide tires, you have lots of rubber. But you have your steering kingpin angle and your axis of rotation. And if you draw an imaginary line between where your top pivot is, your bottom pivot is, and extend that line down to the road, that's your axis of rotation. That's where your wheel is actually going to turn around. Then you also have the point where your tire is actually touching the ground. For a normal car, your tire is really big, so it's almost always in the contact patch of the tire. But for solar cars, those can be very different. So for a demonstration, if you take a can or a cup in front of you and rotate it around itself, and the pivot's in the middle of the cup, you rotate around. It rotates very easily, you don't drag it a lot. But if you move that rotation like 4 inches outside of the can, you're now dragging the can in an arc. You're doing the same thing every time you turn if you have a scrub radius. And when you're dragging these low-performance tires or bicycle tires, even motorcycle tires around, you're doing extra work and adding extra wear to the tire every time you turn the car. You're also making it harder to turn the car. So ideally, you want that axis of rotation to be right in line with your contact patch. Caster. So now we're looking at the car from the side. Caster is how far back or forward that axis of rotation is from the vertical. So we've got the vertical line as the dotted line again, and then we've connected the top pivot and the bottom pivot with the solid red line. So positive caster is generally a good thing. It gives feedback. However, it makes the car a little bit harder to turn, but it also causes the car to self-center. And this is one of the things that was wrong with the car that I set up. So if you have positive caster, when you let go of the wheel, the car is going to tend to straighten itself back out and go into a straight line. The downside of that is it's a little harder to turn. You're going to have to do more effort to turn the car. Negative caster, the car's unstable. It wants to turn. Actually has a force that will try to turn the car when you let go of the wheel. And coming out of a corner or something like that, it won't self-straighten. So you actually have to manually correct it, which becomes difficult. And finally, the most important one, and the one that we see issues with probably the most, is your toe. And we're now looking from the top down, center line of the tire. It's basically the difference in angle of the tire to you going down the road. And so toe in improves your straight line stability. Toe out improves steering response, but can make the steering very jerky. So with all of the things we've talked about, solar cars should be very small in any of these. But again, generally you probably want to be towards neutral. If you're gonna be out of neutral, you probably want it to be very slightly in, but you don't want a lot because if you have toe in or toe out, you're also dragging the tire down the road, and your high efficiency tires are not providing high efficiency for you. Okay, and so measuring toe is a big issue. Fine, but it's actually very easy to do with very simple tools. You can do very expensive lasers and things like that, but if you have 2 sticks, you can measure your toe in or toe out. But it's very important to do it the same way every time. You have 2 points, you can measure the difference between the A's and the B's and do a very complex formula, or measure A, measure B, and you know the distance between those two. You can do math and find out what your toe is. Though really that's not so important. Most people don't actually care what the exact toe is. They just want it set up the same way each time. So doing it the same way. So if you measure it, if you don't do it the same way every time, you can get very different numbers. If you measure that instead of the other one, or measure it that way, you're going to get different numbers or the same numbers and have no meaning. Okay, I don't know where the slide went. Anyway, steering axis, that's out of order. We already talked about it. So the final thing for steering is the Ackerman steering angle. So your car is going to follow a certain path through a curve based on how you turn the wheel. And so you're going to have the center of your turning radius. So anyone know what the required turning radius for the solar car is? 15 meters. So you know what you have to be in. So if you draw a line perpendicular to each tire through your front tires and one parallel to your back tires, that's going to be the axis of which you turn your car around. So if you set your car up with your steering connections, your tie rods connected with a line between the pivots and the center of your back axle, you're going to have it set up so that you automatically get this Ackerman steering so that you're going to turn nicely and not drag the tires around the axis, as you make that minimum turn diameter. And with that, I'm going to give it back to Chris for wheels and tires.
Okay, we got the 2-minute warning, and there's only a couple slides left. So you guys have already heard about wheels. There's a couple of different ways you can go about it. We're going to talk primarily about motorcycle wheels, like junior dragster wheels, and some of the higher end stuff that you can get that's specifically meant for solar car racing. A lot of people have found wheels that are meant for like mopeds and some of the other EV vehicles or other lightweight things out there. 3-wheel design versus a 4-wheel design. The 3-wheel design can be a little lighter. It's easier to align. There is potential for it to be not quite as stable or safe. That's why you see that on the back there. It's very common, though, in our single-seaters. The 4-wheel design cars, they're required for the cruiser division. You can straddle things. Don't be William with a 3-wheel design that straddled every single pothole on the road and hit it with the rear wheel instead until he broke the rear wheel. 4-wheel designs, you know, it's a normal car. And it's much more stable on flat. The weight distribution is a little less critical. These are all factors you want to consider with a 3-wheel design. You need to make sure the car is going to be stable. And if you have questions about that, there are plenty of people you can talk to, including other advisors or us. Talked about the 4-wheel design. Wheel choices, NGM wheels and tires, they're called something now, I think, was it Enlighten? They're not Ucopias. The tires are Enlighten. I think the hubs are still available somewhere, but we also see a lot of motorcycle, junior dragster, and even bicycle components. They have to be able to handle lateral forces, and if you have a 1,200-pound steel car, I do not recommend you take anything from a bicycle and use it, brakes or wheels. So here's just some quick examples. The two on the right are junior dragster type wheels. The one on the left is motorcycle. This is a spoked wheel for a motorcycle. I am not a fan of spokes. They tend to be less aerodynamic, and they tend to not necessarily be as structural as a non-spoked wheel like this, where you've got solid components on it, even if there's a lot of material taken out of the wheel. Weight, when you're thinking about wheels, heavy wheels, they almost become flywheels. So there's potentially a little bit of a penalty if you're doing a lot of start and stopping. If you had a flywheel with a lot of mass around the outside, or polar inertia, even though I just call it the moment of inertia. Anyways, it takes a lot of energy to spin it up, and then you lose it when you hit the brakes. If you're just cruising around, it's a neutral thing, because whatever energy you put into those wheels to get them spinning, as soon as you start kind of coasting up a hill, the energy comes right back out. It's not lost unless you, again, hit the brakes. I already covered solid wheels versus spokes, other than saying that there's an aerodynamic trade there too. The spokes are worse from an aerodynamic perspective unless you're covering them by fairings. And here's the key, less load capacity. Be careful with any spoked wheels you're going to use. I've seen plenty of teams fold them up when they do the slalom test, or fold them up in the, at home before they come to the event. Tire width, we're going to talk about this real quick. Thinner tires, obviously less rolling resistance. The Enlighten tires, the old Ecopia tires, they're very super thin. They're almost like thick bicycle tires. Tiny little patch on the ground versus you think about a car tire or a motorcycle tire where you have a really wide patch on the ground. Less rolling resistance, but also less contact, less stability, less grip for acceleration. So it's a trade there. Just heads up on that. We're only trying to make you aware of it. If you minimize that little contact patch, you minimize energy loss and rolling resistance, but you also minimize stability and grip. Here's just a note too, the tire deforms when it contacts the road. Again, so a smaller patch is better, but even that will deform into this oval shape. That flexing of the rubber eats energy. If you ever wondered where some of the heat comes into tires when the pressure goes up after you've been driving on the road, it's because you're bending the rubber back and forth the entire time you're driving it. And that's one of the places you lose energy. Also a reason for putting the pressure in the tire at the maximum. Brakes, you always have to have two independent braking systems. We already talked about MCP brakes. They're a go-kart brake. They're fairly amazing, easy to get your hands on, and fairly cheap and reliable. I do not recommend any bicycle hydraulic components. I see this with people trying to do ultralight cars, and they tend to have issues stopping. When in doubt, use something that for a go-kart and get a big rotor so that you've got a big lever arm to make sure you can stop your car, especially, again, if it's over 1,000 pounds. Brake pedals. They have to be independent automotive style pedals. It used to be in the past that you can kind of overlap them like this. That is not allowed anymore. You have to have two separate automotive pedals operated by the foot, no hand brakes, nothing homemade. They must be automotive style pedals per the braking rules. So just a heads up on that. And we mean two independent things because if you lose a braking system and they aren't independent, you have no brakes in the car anymore. I have stories about that, but I'm out of time, so I'll share that for another time when I almost killed myself because I forgot to lock nut the pedal in place. Brake testing. We test them at scrutineering both in a static and dynamic situation. Static meaning it's at rest, make you push it, make sure it holds the car in place. Learned that the hard way when I was sitting on a hill in 97 and the car kept trying to roll. No, 98, it was coming out of the speedway. The car kept trying to roll backwards down the hill because the brakes couldn't hold it while we were sitting there without chocks. Dynamic is just when we get you up to 20 miles an hour, ask you to hit the brakes and show that you can stop in under 2 seconds, 3 seconds, what the exact number is in the scrutineering books. Takeaway from this, lots of vehicles have brake problems. Test them before you ride. Did I mention testing before you come to scrutineering? Just checking. Test them before you get here so that you don't have a huge issue with no time to fix it. That's it.